All right, Math 201 students, this is the video for some of the extra examples we had to skip in class from section 3.2 and 3.3. Starting with section 3.2, we skipped number 4 in this group that said find all of the relative extrema for the following function. And I believe I had marked it as number 4 here. So the first thing to remember is that to find your relative extrema, you have to know your first derivative. So that's the first step so that we can find our critical numbers. So f prime of x here would be 4x to the third minus 32. We set that equal to 0 for our critical numbers, and we pull out a 4 since they're both divisible by 4. And then I threw this one in here just to see if you remembered how to factor perfect cubes. For example, the cubed root of x cubed is x, and the cubed root of 8 is 2. So when we factor perfect cubes, there's always a binomial and a trinomial. The binomial is composed of these two roots here and the sign of the original problem, so that would be x minus 2. And then to get your trinomial, you take x and 2 and you just pair them together. So what I mean by that is you do x times itself, which would be x squared, x times 2, which would be 2x, and 2 times itself, which would be 4. Now you do have to have signs in the middle of each of these spots, so the rule for that was SOAP, same as the original, stands for the first sign, opposite to the original stands for the middle sign here, and then always positive for the end. So that is how you factor a perfect cube if you are rusty on that. That's not typically one we would throw at you, but it's good to practice your factoring skills. So this would be a critical value of 2. And this right here, to know if this had any critical values, you'd have to use quadratic formula because it does not factor. So that is x equals negative b, which is the 2, plus or minus square root b squared minus 4ac all over 2a. So sometimes you do need your quadratic formula. So this is negative 2 plus or minus. This would be square root of 4 minus 16. And I know I can stop at this point because this is going to end up imaginary because it ends up being a negative under my square root. So this does not give us any critical values from this because they're not real numbers. So the only critical value that I have to test is the number 2. So we make our number line. We put that critical value right there in the middle. This is the interval negative infinity to 2. This is the interval 2 to infinity. 0 is smaller than 2 and 4 is larger. Remember, when you're doing increasing, decreasing test, you plug these numbers into your first derivative. So I'm just going to plug it into the original because that might be easier. So 4 times 0 cubed minus 32 is going to be a negative. And 4 times 4 cubed minus 32, that's going to be 64 times another 4, which I don't know off the top of my head. So 64 times 4 is 256 right there. So minus 32 will definitely be positive. So this means that we are decreasing on this region and increasing on this region because remember that's representing the slope of the tangent lines being either negative slope or positive slope. And remember we said that if you drew this little picture, this is decreasing until it hits that critical value and then it's increasing. So notice that is a min. So we have a relative min value, remember I always put a blank here, at x equals 2, and to find that value we need to figure out what is the ordered pair that goes with that. So you go back to your original function and you plug 2 in, so 2 to the 4th minus 32 times 2 plus 4, that's going to be 16 minus 64 plus 4, so that ends up being negative 44, I believe. So that would be how I would write it if I wanted to write a sentence. I could also just have someone ask me for the ordered pair, and it would be the relative min is at 2, negative 44. So remember, that's another way you can write it. Okay, so that answers that one. If we go to the next page, we also skipped number 6, which has the same directions, find all the relative extrema. So we want to take the first derivative of this function as well, and then work out that equal to 0 and find our critical values. So this would be f prime of x. That's a little bit too much. that down, equals, the derivative of that would be 2. You got to be careful here. You pull the 2/3 to the front, and the 3 on the bottom would cancel, so that would just be a -2. And then we lose 1 in the power, so that's going to be -1/3 once we subtract 3/3. So that means my actual derivative is 2 minus 2 over the cubed root of x. We're going to set that equal to 0. We want to make sure that we solve for all possibilities, so I'm going to get a common denominator by making this have a cubed root of x on top and bottom, because we don't want to lose the fact that 0 on top or 0 on bottom both could give us critical values. One's undefined, one's where it equals 0. I can pull a 2 out of the top, and that would leave me with cubed root of x minus 1 over just cubed root of x. So cubed root of x minus 1 equals 0 when we add 1 and then cube both sides, because this is a cubed root. If you cube 1, it's still 1, so one of our critical values is at 1. And then we don't want to put in 0 because that would make this undefined. So both of these are critical values. We test anywhere that makes the derivative undefined and anywhere that you have a number that makes the top equal to 0. So we're going to make our line. Put 0 down first since it's the smaller of the two numbers. Got a positive 1. We need a test value for each side, so -1, maybe 0.5, and maybe 2. We're going to plug these into our first derivative. So if you plug in a -1 under a cubed root, so I'm looking at this line right here. This is the one I'm plugging into when I do my chart. Just looks easier to plug into. So if you plug in a cubed root of -1, that's going to be a -1, and then that negative times that negative will make a positive. So this overall region ends up being positive plus 2, so it's positive. 0.5, cubed root of 0.5, let's see what that is. So 0.5 raised to the 1/3 power, since I don't have a cubed root button on my calculator. It's going to be 0.7937. And then I have a reciprocal button, I believe, which will let me to flip that to the bottom. You would have just typed this as 2 divided by that, but I'm just trying to do it on this calculator. Times it by my -2, and then I have to add the 2 up front. So yeah, this comes out negative overall in this region. If we plug in 2, cubed root of 2, so we're doing 2 divided by the cubed root of 2, so 2 to the 1/3 power. Just doing the whole fraction at the same time. So that's this fraction right here, 2 divided by cubed root of 2. And then I'll make that negative and then add it to the 2 out front. So this comes out positive. So just because there was a cubed root here, I kind of had to do some of this on my calculator. So this region is increasing, this region is decreasing, and this region is increasing. Now, the thing about this is, even though this is where the derivative is undefined, as long as 0 exists in the original function, we can still have a relative max or min there. If you have an undefined value in your first derivative and it's also undefined in the original function, it cannot be a critical, or it cannot be a max or min. But since all of these are defined in the original function, then this does make sense that we have 2 different extrema, increasing to decreasing, decreasing to increasing. So we have a relative max value of blank at x equals 0, because that's the maximum. And we have a relative min value of blank at x equals 1. And remember, to find each of those, you have to plug them into your original equation. So f of 0 is going to be 0. F of 1 will be 2 minus, that's still going to be a 1, so that's going to be minus 3, so that's -1. So this is 0 and this is -1. Those are their y values. So another way of writing these, remember, would be 0, 0, and 1, -1. Okay, so that's those max and minimums. All right, there were 2 more that we left out from this video from the section 3.2, and that was to do with absolute extrema. Remember, we said this is a little different. An absolute extrema on a closed interval has to either happen at the endpoints or at a relative max or min in the middle. So when you try to search for these, you're going to have to first of all figure out what your first derivative is and get your critical values. Then you check to see if any of those critical values are in your closed interval. Any of them that are not, you just throw them out. if they're in the closed interval, you don't test them in the first derivative. You test the endpoints and the critical values that are in the interval in your original function, because when you're looking for the absolute max or min, you just care about the ordered pair, the y value. So that's what we do to figure out which one is the absolute max or absolute min. So we had this one right here, number 2 we needed to do, and number 3 as well. So it says find the absolute extrema of this g of x on the interval -5 to 2, round to 2 decimal places for our answer. So this is a not so fun one to take because this has got a chain rule. So we have to do g prime of x, and then we need to pull down the 2/3. So this would be 2/3 x squared minus 1 to the -1/3 times the derivative of the inside, which would be a 2x. I would probably want to rewrite this and set it equal to 0. So 2 times 2 would be 4x on top. Then we have a 3, and then we have a cubed root of x squared minus 1. Okay, so the only place that the top could equal 0 is if x is 0. The bottom, it has to do with this radical part right here, because if the radical ever goes to 0, the whole bottom would go to 0. So think about x plus 1, x minus 1. Either one of those could cause problems. So -1 and +1. Now, out of our interval here, all 3 of these actually are in the interval. So they're all 3 in here. So that means we have to test all 3 of them into our function. So we come over here and we just make a list of g of -5 would be the smallest, g of -1 would be the next smallest, g of 0, g of 1, g of 2. And then we're just going to plug them in. So this would be, and I like to write it this way, the cubed root of -5 squared minus 1 all squared, because that's the 2/3 power right there. This is the cubed root of -1 squared minus 1 squared. This is the cubed root of 0 squared minus 1, and then that's all squared. So I'm just filling these into the original function. And then we'll test to see what's largest and what is smallest. Okay, so this would be 25 minus 1, so that's 24 squared. So this is the cubed root of 24 squared. And I don't even care, I'm going to turn it into a decimal in a minute. So another way of typing that is 24 to the 2/3 power. This one would be -1 squared is 1, minus 1 is 0, so this is just going to be 0. This is -1 squared, which is 1, so this is cubed root of 1, which is 1. This is a 0 again because it's 1 minus 1, so that's going to be 0. And then this one is 4 minus 1 is 3. So this is the cubed root of 3 squared, or cubed root of 9, since that's an easy one to do, which is 9 to the 1/3. So the real question is, what are these two guys to 2 decimal places? And we can use our calculator for that. So 24 raised to the, and if you do this on your calculator, sometimes you need to use parentheses for the exponent. 2/3 power is approximately 8.32. If we round to 2 decimal places. And 9 cubed root of 9, so 9 to the 1/3 is 2.08. So the lowest value, actually, I'm going to highlight this. So my absolute minimums, there's 2 of them. They occur when the graph is equal to 0. That's the lowest this y value ever got, and that happened twice. So I have, let me get a pen back, my absolute min at 2 different points, -1, 0, and 1, 0. And then my absolute max happens when I have this 8.32. That's the largest that this gets. So that would mean that my absolute max happens at -5, comma, approximately 8.32. Okay, so that is that one, number 2. A little bit tricky just because you had the cubed root you had to work through, but you have your calculator. Number 3, again, we're going to be finding the absolute extrema on the interval 0 to infinity for this function right here. First step is, again, to take your first derivative to see if you have any critical values that are in that interval. Make that thinner. So derivative of 4 is nothing, but I do have to do not chain rule, quotient rule on this guy. So I'm going to write this as this was negative 6x, because I'm going to use my negative sign on top just because I have to use it somewhere. And then my bottom function was x squared plus 9. Derivative of that is negative 6. Derivative of this is 2x. So it would be negative 6 times x squared plus 9 minus negative 6x times 2x all over x squared plus 9 squared. So it's going to be negative 6x squared minus 54 plus 12x squared over x squared plus 9 squared. Then my top ends up being 6x squared minus 54 over x squared plus 9 squared. And I'm going to go ahead and factor out that 6 on top. That makes x squared minus 9. That is not the same thing as x squared plus 9, so please don't reduce that. This is a x plus 3 and an x minus 3 on top, and this one is non-factorable because it's only going to factor with imaginary numbers. So this guy is never going to end up being 0 on the bottom. But we do have two critical values of negative 3 and 3 from the top. Now, since our interval is only from 0 to infinity, we throw out the negative 3. So I only have to test two things because this infinity can't be tested. We need to test the first endpoint, which is 0. And remember, you tested in the original function if you're looking for absolute extrema. And then we also need to test the 3. So this is 4 minus 6 times 0 over 0 squared plus 9. That's just going to be a 0, so this is going to be 4. And then the other one is 4 minus 6 times 3 over 3 squared plus 9. That is 4 minus 18 over 18, which is 4 minus 1, which is 3. So the highest one is obviously 4. And the lowest one is the 3. So that means I have an absolute max at 0, 4, and an absolute min at 3, 3, because that's the x value and the y value. Okay, so that finishes up section 3.2. I did want to do one more together on 3.3 to prep us for our next class session. We did this concavity test where we just looked at whether a function was concave up or concave down, and then we defined a point of inflection right before we left class. Remember, a point of inflection is a place on the graph where your concavity changes from either being positive to negative, and that will happen either when f double prime is equal to 0 or f double prime is undefined. The only time it can't happen in one of those conditions is if the undefined part was also undefined in the original function. But usually, you know, the x's ending up in the denominator happens sometimes because of taking the derivative. So we're going to do this one real quick. The answer is already on the graph. Essentially, you can see this is where it changes concavity at 0, 1. But we want to prove that, and I did a couple of these in the notes so that we could prove to you that this makes sense. So the first thing is you want to take, if you're doing concavity and points of inflection, you want to get to the second derivative. So f prime of x here would be 8x squared. F double prime of x would be 16x. So there's no denominator involved. The only place that you could possibly have a change of your concavity is at 0. So we make a chart, put our 0 in the middle. This is negative infinity to 0 and 0 to infinity, because we do want to discuss the concavity. I'm going to pick negative 1 and positive 1. And remember, we are testing this in the second derivative if we're testing for concave up or concave down. So if you put 1 in here, you're going to get 16. So that's positive. If you put in, or sorry, negative 1. On the wrong side. If you put in negative 1, you're going to get negative 16, which is a negative. And if you put in positive 1, you're going to get positive 16, which is a positive. So this is concave down in this first region and concave up. So we want to write that concave down on negative infinity to 0, which makes sense because that's from this point up to here. That's our concave down bowl. And then our other one is concave up from 0 to infinity. And notice the bowl is going upwards this way. And then the point of inflection happens anytime you change from concave up to concave down and the actual value for x exists on the original function. So my point of inflection, POI is what we call it, happens at 0, and we would have to plug it into the original function to figure out the y value, which is positive 1, which we could see that from the graph. but you won't always have the graph in front of you. So I just wanted to at least do one of these that saves us a little bit of class time. All right, that's the end of this video.